First and second laws of thermodynamics, a quick review. First law, total energy conserved in any process, joules in equals joules out. Second law, heat only flows one way, and we can't turn heat into just work, etc. This second law sounds a bit vague compared with the first law. Can it be stated more precisely, more numerically, like the first law? Back to the Carnot cycle. Link to animation. But this time think of it as showing two different routes from A to C, ABC and AT. We know that the total change in a state variable, P, V or T, from A to C doesn't depend on which path we take. But the total heat flow into the gas does depend on path. The amount of heat in the gas is meaningless. Back to the Carnot cycle. However, the heat input QH along ABC is related to the heat input QL along AT. Clausius defined entropy by, the entropy change along a half Carnot cycle is, this doesn't depend on path. What, P, V, path does the gas follow? The initial state is P, V, T, say, and sometime later P/2, 2 volts, T. But in getting from one to the other, it does not follow a path in the P, V, plane. Obviously, P varies within the container. However, the entropy difference between the initial and final states is well defined. Remember, it's defined by a reversible path. Entropy measures occupied space. Each time we double the volume phi the gas can move around in, at constant T, the entropy per molecule increases by KLN2. Entropy is apparently a measure of available space for the molecule to wander around in. But what if we double T at constant V? That certainly increases entropy. We had to supply heat, but the molecule's still stuck in V. So what does that have to do with the space a molecule has to move around in? Microscopic states of a gas. Imagine you wanted to know everything about a gas at one instant. What would that mean? First, you'd need the position of every molecule. You could draw a picture with dots indicating where each one was. But that's not all, you need to know all the velocities as well. You could put lots of dots in a velocity space. Molecular velocities. How does entropy vary with temperature at constant volume? Let's heat an ideal monatomic gas from T to 2T at constant V. Remember when we doubled the volume of space, each molecule had KLN2 more entropy. Doubling the temperature has increased the volume of velocity space by the volume of the sphere having radius odd. This volume has increased by a factor 23 halves. This gives the right delta S. S equals KLNW. Bottom line, the entropy per molecule is K times the log of the total amount of space, ordinary space and velocity space together, the molecule is free to wander around in. This combination is called phase space, written W. This was Boltzmann's great achievement, and his epitaph. Entropy and heat flow. Heat flow between objects at different temperatures invariably causes entropy to rise. Suppose heat delta Q flows from temperature T1 to T2, T1 greater than T2, of course, then. Unless we are trying to heat the cooler object, this is wasting heat which could have been used to drive a heat engine between the two temperatures. No energy is lost in this heat flow, it's just spread around more evenly. The entropy increase implies that the energy is taking up more space. This means, though, that the energy is less available to do work. We can extract useful work from temperature differences, having the energy concentrated in part of the system. Entropy and disorder. Suppose we have a partition box with red molecules on one side, green on the other. We remove the partition and let them mix. Clearly this is more disordered. Think of tossing a coin for each molecule to decide which half to put it in. What are the chances of getting the top arrangement? For 60 molecules, 1 in 260, or about 1 in a billion. It's like the random walk, the chance of every step being in the same direction. And, just as most random walks end near where they start, meaning roughly equal numbers of steps each way, most molecule arrangements have roughly equal numbers each side. The entropy can be thought of as the lane of the number of arrangements of molecules corresponding to the observed macroscopic state. This is the amount of phase space for that state. There's only one left-right arrangement giving the upper picture. A multitude look like the bottom with roughly equal mixing. So, the lower picture is the higher. Entropy. Maxwell's demon. It occurred to Maxwell that a tiny creature he called his demon should be able to decrease entropy, and violate the second law if it were quick enough and could see molecules. It occurred to Maxwell that a tiny creature he called his demon should be able to decrease entropy, and violate the second law if it were quick enough and could see molecules. Feynman's ratchet. A tiny paddle is hit randomly by molecules flying around, but can only turn one way. There's a ratchet wheel. So, maybe the random heat energy of the flying molecules can be harnessed as useful mechanical energy? It works for the first few molecules, but then the ratchet itself gets hot, jiggles around, and the wheel is equally likely to move either way. Bottom line, no machine can be devised, even of molecular size, to just extract heat energy, cooling the gas, and generate work.